All right, good morning, everybody. Hope everybody had a nice weekend. So today we're going to continue on in Chapter 5, and we're going to talk about stereoisomers some more, right? So how does a stereoisomer differ from a constitutional isomer? Pardon? Yeah, so when we're talking about a stereoisomer, we're talking about how the atoms are oriented in space, not how they're connected, right, in terms of like a constitutional isomer. Okay, so constitutional isomers will have different IUPAC names, they will have different physical properties, et cetera, et cetera. Stereoisomers, however, will have the same IUPAC name with the exception of things like cis and trans, or, as we will learn today, R and S, which you all have already covered in lab last week, right? So how to name things in terms of R and S. So we'll talk about that. Now, it turns out that stereoisomers really have the same physical properties in just about all things except optical activity. And we'll talk about that a little bit as well. Okay? So, if we look at the molecules that we have here, on the left we have leucine, which is an amino acid. So for those of you in biology, you should know the structures of your amino acids, right? There's our alpha carbon, as they call it, right? And attached to that are four different groups. We have a hydrogen, we have a carboxylic acid, we have an amino group, and we have this alkyl chain, right? And we can imagine drawing the other configuration. And what do I mean by configuration? Okay, so it's a mirror image in this case, right? And so here we have the same things connected to that alpha carbon, as they call it, right? But what would happen if we tried to take this molecule and overlay it on that molecule? We wouldn't be able to get everything to line up, right? And so they are enantiomers of one another. Just like our right hand is an enantiomer of our left hand. It is a non-superimposable mirror image. Likewise, if we look at 3-bromohexane, we can see that we have two enantiomers, and in fact, they are non-superimposable mirror images. So they are enantiomeric pairs, if you will. So this hand, let's just call that the left hand for lack of a better term, is the enantiomer of the right hand of this molecule. However, if I try to tell you all to go into or pull out your model kits and tried to have you build one, you would need to know which enantiomer I wanted you to build, right? And so we need a way to describe how those atoms are oriented in space that makes a lot of sense. And that's one of the things we're going to be talking about today. I want you to identify the chiral centers, if there are any, in each of the following molecules. How about the red one? Do we have a chiral center? Where's it at? The first carbon. What's that mean? Okay. So yeah, this alkyl halide, if you will, is chiral, right? We've got a bromine attached to it. We've got a hydrogen, which isn't depicted, but we know it has to be there, right? And we know that this carbon, or this group, if you will, is clearly different than this group. So we do have four different things attached to it. We have a chiral center.
The first carbon is the one on the double bond, right?
In terms of you would want the alkene to be named that way, yeah. So we've got a chiral center here. How about with our yellow molecule? No chiral centers, right? Okay, good. And how about here? How many chiral centers do we have, if any? There's definitely one. Which one do you think it is?
The one to the right, the ox.
This one?
Yeah.
Okay, so let's see. Is that a chiral center? We've got a methyl group. We've got a hydrogen. We've got this group. And we've got this carbonyl carbon, right? That's four different things. So that is definitely a chiral center. How about this carbon right here?
Yeah.
It's attached to this group. It's attached to an ethyl group. It's attached to this group, which is different than this group, right? and it has a hydrogen. So it too is a chiral center. So we actually have 1, 2, 3, 4 chiral centers in this particular molecule. And so we would need to star all 4 of those to show, clearly show all of them. All right, so we're going to get into this R and S business. And in R and S, this allows us to determine which molecule we need to draw. So if somebody said R3-bromo hexane, you would be able to draw that in the proper orientation. And if somebody said S, you'd be able to draw the enantiomer of the R very, very easily, okay? And so even though 3-bromohexane is always 3-bromohexane, it can either be R or S. Okay, it can be the right-handed version or the left-handed version, if you will. And we're going to use some rules that come from the so-called Kohn-Ingold-Prelog system, or I call it the CIP system. Okay, and it's really pretty straightforward, but it is some stuff that you're going to have to kind of commit to memory. And so to designate an enantiomer as R or S, you're going to have to identify the priorities on the chiral carbon. You're going to have to prioritize what's attached to it. Okay? And the first rule is based on atomic number. So if I look at this particular carbon, we will all agree that it's chiral because there's 4 different things attached to it, right? And those 4 things all have different atomic number. So we can assign priorities based on atomic number. The higher the atomic number, the higher the priority. So if we look at it, bromine has a higher atomic number than chlorine, has a higher atomic number than fluorine, clearly has a higher atomic number than hydrogen. So we have first priority, second priority, third priority, and the 4th priority.
What's the reasoning behind just, finding that green high for the highest atomic number? Like, is there what's the chemical reasoning behind that? Or is it just an easy way to
It's just, yeah, it's just really.
Is there true rhyme or reason for it? Just kind of, it works.
It does work. I mean, we could have assigned it the other way, and it would have worked just as equally.
Okay, that's probably one.
But the higher the atomic number, the higher priority just seems to follow naturally, right?
Yeah,
Something that's bigger, has more neutrons and protons should be,
I'm good with that.
yeah. So that's how it works, right? So, so we've got that. Okay, so atomic number, easiest thing to do. Now it turns out that until the 1950s-ish, all configurations were actually relative. So if you're in your biology class and you hear about L-leucine or D-leucine or L sugars and D sugars, those are all about stereoisomers, but it was all relative at that time. And that's where the D and L configurations come from. So when you ever wonder where all that, why we have L amino acids and D amino acids, for example, in your biology classes, it all comes from this relative configuration. And the biology people and the biochemistry people never got over the relative configurations. And they just kept it, okay? The fact of the matter is, though, we can now absolutely know the precise arrangement of atoms in space. And in the 1950s, there was an X-ray experiment done that definitively showed how the atoms were oriented in space. And so now we can do this absolute stereochemistry assignments. And that's what R and S are, okay? So that's just a little history there. So if we look at 2-butanol, we're going to have to assign the priorities to the things that are attached to the chiral center. And the rule was what? Atomic number, right? Well, if I look at this and I look and see what's attached, I know I have a hydrogen, an oxygen, a carbon, and a carbon. Well, I can make 2 decisions. I know that hydrogen has to be my lowest priority because there's nothing smaller than hydrogen, right? And I know that my highest of these is going to be oxygen because that has the highest atomic number. Now I have to decide between the methyl group and the ethyl group. How do I make that decision? What's the next step down?
Go to the next element in the molecule, or the next, maybe the next carbon group kind of thing.
Okay, so I've just made my assignment 4 and 1, right? And now I've got to decide which one of these is 2 and which one is 3. what you do is you look and ask yourself what else is attached to this atom. What else is attached to this atom? 3 hydrogens. So you put the hydrogens in parentheses. And you do this in decreasing atomic, from highest to lowest atomic number. So what else is attached to this carbon? A carbon and 2 hydrogens. So I now look, I can't make a decision here because they're both carbon. So now I go into my parentheses, hydrogen versus carbon, which one wins? Carbon. So this is going to be 2, and this is going to be 3, okay? Do not try to do this in your head and keep track of it. Write it out. Use your parentheses, okay? It's the easiest way to do this, okay? So now we were able to determine the priority of the groups when the thing that's directly attached to the chiral center happens to be the same element, okay? So now we have to determine whether or not these are R or S, right? Right now we've got this labeled enantiomer A and enantiomer B, but if I told you to go and draw enantiomer B, you wouldn't know what to do. There's no rules for A and B, right? It's all just a normal label that's just thrown up there. We've just assigned the priorities. We know that the OH is going to have the highest priority. We know that the ethyl group is going to have the second priority. We know the methyl is third. And we know that hydrogen is 4. Now, some websites that you go to will actually make the lowest priority group number 1. I like to play golf with this, right? The lower the number, the higher priority, okay? So number 1 is number 1. That's the highest priority, not 4, okay? So 4 is always going to be your lowest priority. Number 1 is going to be your highest priority. So we've got those situated. The rule after that is you build a model. You grab the lowest priority group. You physically grab it and you turn it away from you to where you're looking down the carbon lowest priority group bond. So you grab it, you turn it away from you. The lowest priority group must be away from you, okay? Once it's that way, if the you look at the priorities of the remaining groups. And what do we see? We see for enantiomer A, it goes 1, 2, 3, and that's in a what kind of direction? That's clockwise, right? So enantiomer A, we go highest priority. Well, let me do this like this. Highest priority, second priority, third priority. So it's like we're turning to the, it's like we're turning the steering wheel to the right. So that's the R enantiomer. And that's how I always remember it. If I'm turning my steering wheel to the right, it's the R enantiomer. If I'm turning my steering wheel to the left, it's the S enantiomer. And you can see here that looking down, we go 1, 2, 3. We're going in a counterclockwise, or I'm turning the wheel to the left, if you will. So we're doing the S, which stands for sinister, okay? So we can turn to the right, which is R. We can turn to the left, which is S, okay? So we can have R, 2 butanol, and we can have S, 2 butanol. Okay, so the R groups are going to the right, the S, they're going to the left. Okay? So clockwise, counterclockwise. Okay. I want you all to take your model kits and build that model. What's the solid wedge telling us? It's coming out of the plane of the screen towards us, and the dashed wedge? It's going behind the plane of the board, right? And everything else is in the plane of the board, right? So all these atoms are going to be in the plane of the board as I have it drawn here. This carbon's the stereogenic carbon. I'm going to have the hydrogen coming towards me, and I'm going to have the OH going behind me. Okay? So let's see what you got. Okay, so Jessica has it built. You can see the projection. So here's kind of the isopropyl group, if you will. This is going to be the hydrogen coming out of the plane of the board. This is going to be the OH going behind the board, and the methyl group, of course, is in the plane of the board. So you can see through this plane how that is, right? It's not a mirror plane, but it's just the plane of the board. So now how are you going to determine the stereochemistry at this carbon? Okay, now that's one of the, which one's the low priority group? You always grab the low priority group. But the first thing that we need to do is assign priority, right? So what priorities can we assign here? Hydrogen is 4. OH is going to be number 1, but I can't make a decision here or here just on those 2 atoms, right? Which one's going to take highest priority, this one or this one? This one? And why? That's right. So if I look at it, this only has 3 hydrogens attached to it. This has 2 carbons and a hydrogen. This is going to win. So this is going to be group 1. This is going to be group 2. This is going to be group 3. And this is going to be group 4. So now grab group 4 and turn it away from you. And now go 1, 2, 3. Which way does it go? It goes counterclockwise. So that's like turning my steering wheel to the left. So it is an S enantiomer. Okay? That is the S enantiomer of that particular molecule. It's like, look at it, like that. Priority 1, priority 2, priority 3. So it's going in a counterclockwise fashion. This is very, very important because if you look at it like this, how does it look like it's going? It looks like it's going 1, 2, 3. It looks like it's going to the right. But that's wrong. Why? Because the lowest priority group's not facing away from me. It's just like telling time in London. If you are walking outside and you see Big Ben, which way does the time go? Clockwise, right? If you're inside Big Ben looking out, how does it look like time is going? Counterclockwise. Time doesn't go backwards inside Big Ben. You're just looking at it wrong, right? The same thing happens here. You all will probably make this mistake on your homework because you'll think, I don't need to build a model. And you will look at that and you'll go, okay, 1, 2, 3, that's going in the R direction. But you're looking at it wrong. Always build a model. I have gotten, after 20-some years, where I can look at this and go, but I know that has to be S. But if you'll build a model and you'll actually grab that 4th priority group and turn it away from you, you'll never get it wrong. Okay? Most of the time, people miss these types of questions simply because they didn't take the time to build a model. Or they built the wrong model. Make sure that the model that you build matches the model that's depicted on the screen or on the page. Okay? Now, it can get a little more complicated when you have other types of functional groups, things that have pi bonds. So for example, how do we count a carbon that's doubly bound to an oxygen? Well, that's like a carbon with 2 oxygens bound to it. Okay? So you have to take that into account. Okay? If you have a carbon that is doubly bound to a carbon, it's like a carbon with 2 carbons attached to it. A carbon-carbon triple bond is like a carbon with 3 other carbons attached to it. Okay? So when you're looking at going out and trying to make those differences, you have to pay attention to the pi bonds. Okay? And treat a C double bond O as a carbon with 2 oxygens attached. Okay, so for example, let's take a look at this molecule. This is Ritalin. Ritalin has actually 2 chiral centers, but you can only determine the stereochemistry of one from this drawing. Why?
Because we don't know the bond, you'll have the wedge bond stuff for the
That's right.
ester.
So in this particular chiral center, you've got three-dimensional representation. You can determine how things are oriented in space. This chiral center I haven't depicted, right? So you can't identify whether it's R or S, okay? So let's just focus on this one chiral center. Everybody will agree that that's chiral because we got 4 different things attached to it, right? And we have to prioritize carbon, carbon, carbon. I can't make a decision based on that, right? So what do I have to do? I have to look and see what's attached to each of those carbons, right? What's attached to this carbon? 3 oxygen. Oxygen, oxygen, oxygen. So I would put up here in parentheses 3 oxygens, right? What's attached to this carbon? 3 carbons. Carbon, carbon, carbon. Right? What's attached to this one? A carbon. And what takes precedence, carbon or nitrogen? Right, so I would put nitrogen, comma, carbon, comma, hydrogen. So now I'm looking in the parentheses. Oxygen, 3 oxygens, 3 carbons, a nitrogen, a carbon. What's going to be priority number 1? This one. What's going to be priority number 2? What's going to be priority number 3? That's right. So 4 is away from me. I did that to make it easy. So we go 1, 2, 3. What way is that? That is S. That is counterclockwise. I'm turning my car to the left, right? And so that particular chiral center in Ritalin has the S stereochemistry, okay? But notice we couldn't make the decision based on the atom directly attached to the chiral center, other than hydrogen, right? Because everything was carbon. We had to look and see what else was attached in order to get the priority using our CIP rules, okay? Now there are some physical properties of these stereoisomers that you need to know about. If we have a 50-50 mixture of both R and S enantiomers of our molecule, we say that it's a racemic mixture. It's a racemate. It has half of it is the R enantiomer, half of it is the S enantiomer. Real easy to make, just like that thalidomide example that we talked about last time. It was given to pregnant females as a racemic mixture. One enantiomer, right, treated morning sickness. The other enantiomer caused severe birth defects. Okay, so it was a problem to give racemates. Okay. A racemic mixture is said to be optically inactive. That is, it doesn't rotate the plane of polarized light. And we'll talk a little bit about that in just a moment. Okay. But it turns out that if we look at enantiomers, so let's just say we have molecule A and molecule B, which are enantiomers of one another. If I have pure enantiomer A, the melting point will be identical to B. So if I take R2-butanol and I take S2-butanol and I get the melting point, and I look at them, they will be identical. Okay? If I have the racemic mixture, the melting point can actually be different, okay, than either one of them alone. That's called melting point what? You all did the melting point lab, right? What happens when you contaminate something? What happens to your melting point? It gets lower and broader, right? And so basically this is what's happening here. The boiling point of enantiomers are identical. So if I take the boiling point of S2-butanol and the boiling point of pure R2-butanol, I would notice that they are actually the same boiling point. However, the boiling point of the racemic mixture may actually be different. If I look at the optical rotation of an enantiomer, of an enantiomer, and I look at the optical rotation of another enantiomer, they will be equal in magnitude but in opposite directions. That is to say that one enantiomer will rotate the plane of polarized light in the clockwise direction, but the other enantiomer will rotate the plane of polarized light in, say, a counterclockwise direction. But the magnitude will be the same. In other words, if this enantiomer rotates at 10 degrees, the other enantiomer will rotate at 10 degrees, just in the opposite direction. And a racemic mixture always gives an optical activity of 0. Does that make sense? They're canceling each other out. That's exactly right. So if I have one enantiomer that rotates equal but in opposite magnitude of the other enantiomer, if I have a 50-50 mix, all the rotation that occurs from one enantiomer is going to be canceled out by the rotation of the other. And so you're going to see no rotation in optical plane polarized light, which we'll talk about here in just a moment. Now this has some real day-to-day kind of practicality, these enantiomers. Okay? S-carvone and R-carvone. They are identical molecules except for the configuration at this particular carbon. Okay? I think you all will agree that caraway smells different than spearmint. Caraway seeds, it's just a seed. It's used in some cooking. Okay? Very different odors. Same molecule, just different configuration. Okay? S-carvone, S-stereocenter, R-carvone, the R-stereocenter. Why do you suppose that these give rise to different odors? All right. How? The molecule never makes it to the brain. It's an electrical impulse, right? So why is it that this gives a different impulse from my nose to my brain than this one? That's exactly right. The receptors are shaped differently, right? So if you have a receptor in your nose, it's made up of proteins, which are made up of chiral molecules, which have one hand. It's just like my glove and my hand analogy, right? My right hand fits into a right glove very nicely, but my left hand does not, right? So if I have a receptor, which we can think of as a glove, I have a right hand and a left hand, they're not going to fit the same, and they actually give rise to a different signal that my brain registers, okay? Because they are different complexes, okay? There are some important things for you all health-wise, okay? So, for example, ibuprofen. It's the S-ibuprofen that's actually the anti-inflammatory agent. When you take Advil, it's this enantiomer that actually gives you the effect. Now, it turns out that ibuprofen comes to you as a racemic mixture, and they've shown that the R-ibuprofen has no effect. So half the drug that you're taking is just being excreted and not doing anything, okay? Yeah?
Does that count in the milligrams? Like it's a 200 milligram?
If it's a 200 milligram tablet, 100 milligrams of it isn't giving rise to the analgesic effect that you're after. Huh? So take two? We can't really, give.
I want to see 6 in 24 hours.
Okay. Fluoxetine, this is an antidepressant. Notice it's a chiral molecule. And the R enantiomer is what you would buy if you actually had to utilize this molecule. Naproxen, if you buy a leave, this is very, very important. This is why you pay a lot of money for chemists to do their job, because it turns out that if you read the back of a leave, it actually says S-naproxen sodium salt. It's not a racemic mixture like ibuprofen, and there's a darn good reason for it. S-naproxen is actually the anti-inflammatory agent. Hurts your aching joints, cures your headache, yada, yada, yada. If I gave you a racemic mixture of this, R-naproxen is a very potent liver toxin. Killing your liver is not a good idea, right? So you really rely on a chemist knowing how to make not only naproxen, but the S enantiomer and only the S enantiomer to put in your pills. If you get any R-naproxen in the medication that you take, it will slowly attack your liver, okay? So, yeah, this is kind of important, right? Cure my headache, kill me. Just because we change the configuration at a single carbon, okay? And so how in the world do we synthesize a molecule that has this particular orientation in space? Huh? Make a filter? That's not far from the truth, actually. It's a little more complicated than that. But, yeah, essentially, they do make it racemic, and then you isolate the S-naproxen, and you throw the other stuff away. In terms of other types of drugs, methamphetamine. Okay, now why in the world am I talking about methamphetamine in this class? Okay, all right. I actually happen to like Walter White. Watched Breaking Bad a lot when it was on. Okay, it turns out that methamphetamine can either be an illicit drug or actually very beneficial, depending on which enantiomer you're using. So, for example, this is the Walter White stuff. It's the S-methamphetamine that is responsible for the high and all the stuff that comes along with methamphetamine. Street methamphetamine, however, is racemic. So somebody that's out buying it on the street, they buy a gram, only 500 milligrams of it's actually going to be responsible for the illicit effect. However, the R enantiomer, you can go and buy right now at Walgreens in a Vicks Vapo inhaler. And it will say on the back, Lev methamphetamine. Lev meaning that it rotates in a liberatory fashion, the optical plane polarized light. Okay? These are identical molecules in all respects except how they're configured at that particular carbon. Right? So what does this do? It opens up the blood vessels, or opens up the, not the blood vessels, the passageways so that you can breathe better. So if you've ever used a Vicks Vapo inhaler, you've taken meth. Okay? It is just R methamphetamine, okay? And you don't get high sitting there snorting on the Vicks Vapo inhaler, right? It does not give that response, okay? In fact, we were doing some stuff in the lab one time and we actually needed some R methamphetamine. We actually went and bought a bunch of Vicks Vapo inhalers from Walgreens and we extracted out the methamphetamine from them.
So people who do like the R meth, will they have the same effect as the Vicks as well as the high?
Are you talking about if it was a racemic mixture?
Yeah.
They would be able to breathe very nicely.
How do you use meth? Like, do you inject it or like do you?
I'm not getting into any of that.
Like, if you inject it, you're not going to get the vapor, you know, like when you.
You can research on that on your own. I'm not.
Say what it's like,
There you go. But the point here is that when you hear the word methamphetamine, you all think about a bad drug. It's not all bad, right? R methamphetamine actually has a very good use, right? And in fact, we think it's so safe, we allow you to walk into Walgreens and purchase a Vicks Vapo inhaler and walk out and nobody ever says anything to you about it, right? Right? You will not walk out of there with a racemic mixture though, because they have to check that. Okay, so there are legal manufacturers that make the R enantiomer of methamphetamine to put into drugs. The S enantiomer is actually controlled substance.
So they're literally throwing away meth whenever they make it. You know, because whenever you make it, it's like it makes it 50-50.
No, they have ways of only making the R. Yeah, because you don't want to deal with throwing this away because that's a controlled substance.
Yeah. That's why
Right.
I was like, I wonder how that would go for the FDA.
A little bit in somebody's pocket here and there, probably. Okay. When we extracted this from the Vicks Vapo inhaler, it was crystalline. Okay?
So you can make the other kind and sell it as the cheap people, right? I'm just saying.
All right. Let's talk a little bit about polarimetry. Now, did you all do the polarimetry experiment? Yes. All right. So you know a little bit about this. It turns out that plane polarized light will rotate in the presence of a chiral molecule if it's not racemic, right? So let's think about the experiment for just a moment. You have a light source, and that light source, if you think about ordinary light, the waves of the light are going in all directions, right? How many of you have ever had fancy sunglasses that you use when you go out on the lake to cut down the glare, right? Polarizing lenses. That's exactly what we're doing here, okay? The reason that those sunglasses work is because they only allow certain planes of the light to come through. And it turns out that glare is planes going everywhere, okay? These waves of light are going in all directions, okay? But you can buy these fancy polarizing filters or polarizing lenses that allow only certain components of the light to pass through. And in this case, just for convenience, we've chosen the vertical component, okay? And so we've blocked out all the other stuff. We're allowing the vertical component to come through. In the presence of something that is not chiral, that plane will pass through the sample and come out the end completely unchanged. So it's the vertical plane coming through, it's still the vertical plane coming out, Nothing happens to it, okay? Would read 0, right? No rotation, okay? And we say that it's optically inactive. So water is optically inactive. A racemic mixture is optically inactive, okay? However, if we place a sample tube full of a chiral compound, what you would actually observe is that the plane of polarized light rotates. And how do we know that? Well, we know what plane is coming through, and then we have an analyzer on this side, and we turn that analyzer until we can see the light. And we notice that the angle of this and the angle of this are not the same anymore, so we can actually determine, okay? And so as the light passes through the sample, it gets rotated either to the left or to the right, depending on the configuration of the chiral molecule, okay? And we call this optically active. It rotates the plane of polarized light, okay? If you ever have a moment, actually on Wednesday we're going to do a demonstration in class doing this to show how this works, okay? But if you have some polarizing lenses at home or a couple pairs of sunglasses, take them and hold them up next to one another and rotate them, and you'll see it gets dark and then light because of that. And so it's the same type of principle here, okay? And so we can actually measure this angle, alpha, which is known as the observed rotation, okay? Now, it turns out that how much rotation occurs depends on several things, okay? It depends on the path length, and it depends on the concentration. The more molecule you have, the more concentrated it is, the more rotation you get. The longer your sample tube, the more rotation you get, okay? So the observed rotation is dependent on these two things. And so we set an equation up to where we have alpha in bracket, which we call specific rotation, which actually takes into account the path length and the concentration and allows us to have kind of a, a parameter for a particular molecule, okay? So it's real simple math. Alpha is just the observed rotation in degrees. The path length is the length of the sample tube in decimeters. And organic chemists love to make things real simple, so we always choose a 1 decimeter tube, which makes the math real easy. But it doesn't have to be a 1 decimeter tube. And then the concentration ain't really a concentration. It's in grams per milliliter. That's by definition from 150 years ago, 200 years ago when this experiment was originally done. Why is grams per milliliter not a concentration? Yeah, it doesn't take into account moles, right? So a gram of lead and a gram of hydrogen ain't the same number of moles, right? It ain't the same concentration, so to speak, right? But this is by definition, okay? So, and we're going to deal with concentration in grams per milliliter, okay? So if I know the specific rotation, and I know the observed, and I know the length, I can determine concentration, right? I just have to do a little algebra. You all can do that, right? So you can rearrange that equation to get concentration. And it turns out this is very, very important for an industry very, very close to home, right? In Louisiana, they like to grow this stuff called sugar, right? Sugar is a chiral molecule. It rotates plane polarized light. Well, if I'm buying a trainload of sugar for my company, I want to know how pure that sugar is, right? I want to know, are they giving me pure cane sugar or are they giving me some inferior stuff, right? And the way that they actually do this is through optical rotation. They have a machine that's a polarimeter, and they make a certain solution of the sugar, and they pour it in there, and they measure how much it rotates plane polarized light. And they know that pure sugar should rotate plane polarized light by a certain amount because they can determine the concentration, right? So you know how much sugar actually rotates, you know your observed, you know the path length that you use. And I believe in the sugar industry they actually use a 2 decimeter tube for whatever reason. And you can determine the concentration very, very easily. It turns out that many, many moons ago, this was also very useful for determining blood glucose concentration, right? If you were diabetic before you had these fancy strips, how in the world did they determine how much glucose you had in your blood? Well, one way to do it would be through optical rotation, because glucose is chiral. It rotates plane polarized light. But it's kind of a pain in the rear because you got to get rid of all the red blood cells. You got to do all this other stuff that could interfere. Okay, but you could determine blood glucose concentration pretty easily that way. Okay, so let's do a sample problem. Everybody get together and work on the math here. So we have a solution of an optically active substance that was made by dissolving 10.2 grams of the substance in water to make 1 liter of solution. The solution was then placed into a polarimeter tube that was 1 decimeter in length. The sample was then warmed to 26 degrees Celsius, and the polarimeter indicated that the sample rotated the plane of polarized light at 589 nanometers by negative 13.62 degrees. What is the specific rotation of this substance? And by the way, 589 is known as the sodium D light, which is D-line, which is typically the wavelength of light we use in these experiments. So what's the equation we need? That's right. So what do I know? I know everything, right? I know everything. So I know that is negative 13 point what? 62. I know the length is 1, and what's my concentration? Which is what? Grams per milliliter. Do the math. 0.2. That's going to be close enough. It's not going to make that much difference in the math. So what's the specific rotation? When we do that math. No, it's going to be negative. Negative what? Close enough. This really likes to rotate plane polarized light. Most chiral molecules, the specific alpha will be like 10 degrees, 20 degrees, 50 degrees. But there are some molecules that will actually rotate. That means that the plane had rotated through 360 degrees many times to get through that sample tube. It had a lot of what we call optical rotatory power. Okay? So, what are you going to be responsible for? Well, you can be responsible for this type of simple math. You can also be responsible for finding one of the unknowns. I could give you any kind of problem and ask you to solve for the unknown. I could ask you to solve for the concentration. I could ask you to solve for the path length. I could even ask you to solve for the observed rotation, what it must have been, okay, if you knew those things.
You'll give us 3 variables, solve the board.
I'll give you enough stuff that you could get 3 variables. I didn't give you all 3 variables here. You had to figure out what some of them were, right? Okay. It turns out that there's another term that we use when we're talking about enantiomers, and that's enantiomeric excess. This tells us how pure our sample is based on optical purity. How much of one enantiomer we have over another. A very, very important number for you to have if you're a medicinal chemist making naproxen, for example, right? I want just 1 enantiomer in my naproxen sample. I don't want any of the R naproxen. I don't want my liver to go bye-bye, right? So it's very, very important to know those type of data, okay? So we historically use what's known as enantiomeric excess, or EE, also known as percent EE. It is the percent of one enantiomer, the major enantiomer, minus the percent of the other enantiomer. So if Sarah made a sample that was 75% of the S enantiomer and 25% of the R enantiomer, what's the EE? 50%. It's a 50% EE synthesis, okay? Would she be able to take her naproxen sample and sell it to you? No, because it'd kill you. What if you made 90-10? 90% one enantiomer, 10% the other. What would the EE be? 80%. Still wouldn't be able to sell it to you. Okay? What if it was 95-5? 90%. What if it was 99-1? 98, still not good enough. Okay, for something like naproxen, you have to have greater than 99.99% EE. It has to be essentially optically pure. Tough to do. Not impossible, they do it. But it adds to the cost. Okay? So it turns out that that number is very, very important. We have to be able to determine it. And it turns out it's real easy to determine using optical purity, or that's why we call it optical purity. You can figure out what the specific rotation is for the mixture that you made. You divide it by the specific rotation of the pure enantiomer and take it times 100, then that'll give you % EE. Okay? So you can determine the enantiomeric excess pretty easily from just a couple of optical measurements. Okay? So let's do one last sample problem. A synthesis was carried out to produce a compound of medicinal value. The optically pure compound is known to have a specific rotation of 112 degrees. A 1 gram sample of the synthetic compound was dissolved to make 1 milliliter of solution. When the solution was placed in the polarimeter tube, the observed rotation was found to be plus 5.6 degrees. What is the EE of the synthetic compound? What do we have to do? I know the specific rotation for one pure enantiomer, right? Now what do I have to do? I have to find it. But what do most people do when they try to do this? They take 5.6 and divide it by 112. That's not the right answer because this is an observed rotation. So we have to convert this into a specific rotation. So I know my observed rotation, I know the concentration, I know the path length, I can figure that out. And then I divide those two numbers, right? Those two specific rotations, and I can get the EE. All right, let's call it quits there for today. See you all on Wednesday.
Wouldn't the observed be the same as the specific rotation?
Well,
estimator times one concentration. I know, but
I rigged it here, yeah. But